we will talk a little bit about mechanical work or expansion work. From your classical mechanics, you must remember that the amount of work done is equal to the force multiplied by the displacement. If you consider a gas confined inside a piston, the gas has a pressure of P, the external pressure is PEXT, and the area of the piston is A, and the gas expands a little bit against this external pressure so that the piston moves by a distance dz, then the amount of differential work done is equal to the opposing force multiplied by the displacement. Now, since the system is doing work when the gas expands, it loses energy, and therefore we put a negative sign in front of this work. What is this external force? This is nothing but the external pressure multiplied by the area of the piston. Remember that the units of pressure are Newton per meter squared, and if you multiply that by the units of area, these two cancel out and you get units for force. The area multiplied by the differential movement of the piston is the differential change in volume of the gas. Thus, the amount of work done is equal to the external pressure multiplied by differential change in volume. Now, we are going to calculate this work for three different cases. The first case is work done against a constant external pressure. The second case is for a reversible expansion of the gas. And the third case is for a reversible expansion but also isothermal. So, let us take the first case, a constant external pressure. The total work done by the gas or the system is equal to an integral of dW, and this is equal to the external pressure multiplied by a differential change in volume integrated from the initial volume to the final volume. And since the external pressure is constant, this will come out of the integral, and the only thing you are left with is the external pressure multiplied by the change in volume. So, this is the amount of work done by an expanding gas against a constant external pressure. If you were to plot this on the pressure volume diagram, so if you have pressure on the y axis and volume on the x axis, and let us say this is the external pressure and this is the initial volume. Remember that this is not the internal pressure but the external pressure, and if the external pressure remains constant and the system expands and you reach the final volume Vf, then the total work done is simply the area of this rectangle. So, this is the amount of work done at a constant external pressure, and this pressure here is equal to P external and not P internal. The second type of work we will talk about is for a reversible expansion. Now, what is a reversible process? A reversible process is a process whose direction can be changed by a slight change in some state variable of the system. For example, you could have two compartments, and the temperature of compartment 1 is T1 and the temperature of compartment 2 is T2. So, if T1 is greater than T2, heat will flow in this direction. If, on the other hand, T2 becomes greater than T1, then heat flows in the other direction immediately. So, if I can switch my temperature slightly so that T2 becomes slightly greater than T1, then the direction of the heat flow changes, meaning that this is a reversible process. So, a reversible process is also often very close to equilibrium. It is the closest you can come to equilibrium. For an expanding gas, a reversible process is achieved when the internal pressure, which we call P in now, is very close to the external pressure, and the gas expands very slightly when P in is very slightly greater than the external pressure. So, the amount of work done, which we previously defined as this, will now change to P dV, where P now is the same as external pressure because this is a reversible process, and this I should change to initial and final volumes. So this is the amount of work done by this gas under a reversible expansion. So that is case 2 right here. If the expansion also takes place isothermally, then this expression can be simplified. We remember that PV equals nRT from the ideal gas law, and then we can substitute P into this equation. So we can write this as the integral over the initial volume to the final volume, and instead of pressure we can write nRT by V multiplied by dV. And then you can, since the temperature is constant, these constant terms come out of the integral, and you are left with minus nRT log of the final volume divided by the initial volume. So let me write this entire equation on the top. The work done by an expanding gas in a reversible isothermal expansion is equal to minus the number of moles, the gas constant, temperature, log of the final volume divided by the initial volume. Okay, so this is the amount of expansion work done by a gas under a reversible isothermal expansion. Now, if the final volume is greater than the initial volume, this implies that log of Vf by Vi is the log of a number which is greater than 1, and this is a positive number. Therefore, the work, which is minus nRT multiplied by a positive number, is negative. Minus VE means negative, which means that the system does work on the surroundings when the gas expands. The opposite applies when the gas is compressed. So the system does work on the surroundings do work on the system when the gas compresses. In that case, the initial volume is greater than the final volume since the gas is compressing, which means that log of Vf by Vi is equal to the log of a number less than 1, which is a negative number, which means that the work is positive. So the work done by the system is negative and the work done on the system is positive. So these are the 3 different types of work. Let us try to plot this reversible expansion onto the pressure volume diagram. This is your pressure, and here we have volume. And since the temperature is constant, we are looking at an isotherm. So you start with an initial volume here, Vi, and you end with a final volume, Vf. Notice, because the gas is expanding, the volume of the gas is increasing, so the pressure is decreasing. The work done for this process is, of course, minus PdV from Vi to Vf. This expression is nothing but the area under the pressure volume curve. So this is the amount of work that is done during a reversible, in this case an isothermal expansion. If the expansion was not reversible, for example, done against a constant external pressure, then if you remember, the amount of work would look something like this. So this is against constant external pressure, and this work is isothermal reversible work. What you can clearly see here is that the reversible expansion work is always greater than non-reversible work. We will talk about these things more in class and discuss some examples.